All right, so we've now spent some time talking about action integrals where I'm doing an optimization problem over a functional, this integral of f, which takes as inputs functions y that are functions of time. They might also be functions of their first derivative. And we worked through a procedure to determine when this integral is optimized. And it is optimized when the function for that particular path satisfies what's known as the Euler-Lagrange equation. That the partial of this function with respect to y essentially is equal to the time derivative of the partial with respect to y dot. A solution to that differential equation is a path such that the action integral on the left is optimized or minimized or whatever you want to be. So again, I'll just quickly note that this minimizes or optimizes s, which is the integral of f dt. This is not minimizing f itself, right? It's not a Calc 1 problem where I'm saying that I'm finding, say, a max and min for f for a given path. But I'm minimizing the action integral where I'm evaluating f across various points from, say, some starting point A to some ending point B. So you can think of it as it is plucking out the path, such if I'm starting at A and ending at B, you can think of the integral as you're taking tiny little steps as you start from A and work your way over to B. And every time you take a little step, you have to evaluate all the possible directions you can move. And each of those little directions is going to involve a little piece of action, the integral of f dt for that little particular step. And the actual path that's taken from A to B is the one that for every one of those tiny little steps, it determines which of those little steps is going to minimize or optimize the action. And then you get a bunch of those optimal little steps, which then traces out ultimately the optimal path. So, and then we looked at examples of, for example, that the shortest distance between 2 points is a straight line, for example. Let us now go back and tie this finally to physics, what's known as Hamilton's principle. And through careful studies that have later kind of been proven, through quantum mechanics, we now can say that a particular system evolves such that what? Such that between two different configurations, a particular integral is optimized. So such that between two configurations, the integral s, which is going to be an integral over this symbol, which I'm going to use kind of a script L to write down dt, is optimized. What is this L? L in this case is the kinetic energy minus the potential energy. And this is called the Lagrangian. So not the sum kinetic plus potential, but the difference of kinetic minus the potential is what's defined as the Lagrangian. That, when you do the action integral between 2 points, is optimized between the 2 points. And again, this is not saying that the value of the Lagrangian itself is optimized, but that the integral of the Lagrangian from one point to the next is optimized. So what is this Lagrangian? Because it seems like it's very close to the total energy, but I've thrown in a minus sign, right? I might say, well, I know the total energy is supposed to be T plus U, right, which is, of course, just total energy of the system. But again, if you can imagine, if we're trying to do an optimization as you go from one point to the next, if I'm in a condition where energy is conserved, no optimization can really occur for the energy because the total energy is constant in a conserved system. And so if I'm doing some sort of time integral of the energy from one configuration to the next, right, no optimization can really take place with the energy because the energy is not changing. It's just going to be an integral of a constant over time. So the energy is not really something, that can measure, that can dramatically evolve as you evolve from configuration to configuration, even when energy is being conserved. The Lagrangian T minus U is, you might think of it as a measure of the liveliness of the system. Maybe liveliness in quotes of the system. Because if you think about it, right, if you have a system where there is lots of motion going on, well, lots of motion is going to apply a large kinetic energy. That's going to imply that L is large in this case. The Lagrangian is large. And that's versus if there's not a lot of motion going on, but all that energy, rather than it being kinetic energy, is kind of locked up in potentials, right? The potential for gravity to do something or for the spring to do something, then L in that case might be, small in quotes. So I always get confused, right? If you have something that's very, very negative, right? If T is very small but U is large, right, the Lagrangian would be a very negative number. Which I don't know, do we call that small or just very negative? In this case, the energy is kind of locked in U, right, the potentials, which could then be tapped to create a more lively system. And so what nature is doing, which is remarkable that this can be proven, that this is what nature is doing, is that, again, let's take the example of a falling ball. So you have a ball that starts here and it ends, eventually hits the ground. Of course, we know the actual path it takes is one that just has it fall straight down. It could, of course, have taken a variety of different paths that could have eventually had it, eventually reach that same point. But of all those various paths, it's taking one very specific path and it is navigating through configuration space, right? How all the possible ways a single ball can be configured. And since it's only a single object, right? Configuration space is kind of the same thing as physical space. The optimal route it's taking is one that optimizes the Lagrangian over time. Right? How does it reach some sort of max-min inflection point of this particular integral? Let's do it as an example first, and we'll see that it really does pop out the right equation of motion. So let's suppose, let's first ask ourselves, what is the dimensionality of this configuration space? Well, I have one particle, and I have it really only moving in one dimension, up and down, and then I have no constraints really acting on the ball. So I expect the dimensionality to be 1. So I need one variable to describe where this ball is. So if I use Q as kind of my generic variable, I'm going to let Q be Y in this case. If I tell you the height of the ball off the ground, and we'll take 0 to be the ground, right, that tells me the location, the entire configuration of this particular system. The Lagrangian then is T minus U. And so U in this case, I expect to just be mgy. I'll define the reference point to be the ground as well, right? That you're of course free to decide where u equals 0 is. And then the kinetic energy is 1/2 mv squared. But in this case, since it's only moving in the vertical direction, this is just 1/2 m y dot squared. Right, since the vertical motion is the only motion that really occurs. And let's suppose we're, as initial conditions, that y at t equals 0 is at a height h off the ground, and y at some later time, t final, is when it finally hits the ground. Right? Those are my two configurations I'm moving between. Well, in this case, the Lagrangian is then going to be t minus u, which looks like it's going to be 1/2 m y dot squared minus mgy. You have to always remember it's minus the potentials, especially if the potentials themselves have negatives in it, right? Be careful that you get your signs right. And this is the Lagrangian for this particular system. Yes, in this case, energy is also conserved, right? So the 1/2 y dot squared plus mgy, the total energy, I might expect that to be a constant, but I don't expect this difference to be a constant. Right, you can think just as a quick example, if it starts from rest at the top, right, the Lagrangian is some negative number at the top, but then as it falls to the ground, it gains kinetic energy but loses potential energy. Eventually y equals 0, but y dot is going to be some number, so the Lagrangian is going to start negative and then become positive. And again, we're not trying to optimize the value of the Lagrangian, but we're optimizing the integral of the Lagrangian as it goes from top to bottom. So now I need, then Lagrange's equation says that the partial of L with respect to y minus the time derivative of the Lagrangian with respect to y dot equals 0. So now I have to evaluate all my partial derivatives. So the partial of L with respect to y looks like then it's just going to be negative mg. And then the partial of L with respect to y dot looks like it's going to be just my dot once I take the partial. Then I have to take the time derivative of that thing. So then I take the time derivative of my dot. And notice that that then just becomes my double dot. And Lagrange's equation ultimately says that negative mg minus my double dot equals 0. Or my double dot equals negative mg, or, and look at that, y double dot equals negative g. The same equation of motion as we would have expected if we did this with a Newton's law problem. Right? It gave us the same equation of motion. But I really had to say nothing about forces acting on the system. Really, I was just talking about, if I can write down the Lagrangian, which involves its kinetic and potential energies, then the path that the ball ultimately takes that will optimize this integral is the one such that the path satisfies this particular differential equation. So then, of course, that then gives us a solution of y as a function of t is negative 1/2 gt squared plus at plus b for constants of integration a and b. And then you could have your initial conditions that lets you get the values of a and b. Right, for example, I could say y of 0 equals h. So then that says that's equal to b. And then y at some final time equals 0. So then that seems to equal 1/2 g t final squared plus a t final plus b, which was h. And then that could then get you a as well. It looks like then a would be, I guess, 1/2 g t final squared minus h, all divided by t final, right? Would be some constant, whatever that is a. And this was an example where I had a starting point and an end point to try to motivate, again, the idea of I'm going from one configuration to the next. But notice the only thing that Lagrange's equation told us was this. It really only gave us a differential equation that we could then solve. And for a given set of initial conditions or boundary conditions, that then gave me the path. Right? I could have also solved. I didn't need to have a starting and endpoint. I could have solved instead the same problem with, say, at y at t equals 0 equals h, and maybe y dot at t equals 0 is some v naught. Right? Nothing would have stopped me from using that as my initial conditions as well, in which case that would imply y as a function of time is negative 1/2 gt squared plus v naught times t plus h, right? The usual kinematic equation. Nothing too surprising there. So again, by writing down the Lagrangian and then employing it, right? Writing down the Lagrangian for this particular system, employing then Euler's equation allowed us to get, ultimately at the end of the day, a second order differential equation, which in this case we can easily identify matches the same thing we would have gotten for Newton's laws of motion. The solution to that optimizes this action integral. That then gives me the actual path the thing travels for a given set of initial conditions. And so I guess I could say just a quick aside on what we are really doing when we're talking about when we're going from one configuration to the next. Because I think it's easy to get confused if when I'm talking about how I go from configuration A to configuration B, where B is kind of the end configuration, it seems like I kind of took that as I knew it in advance, right? The ball starts in the air, ends on the ground, all right? But isn't that end configuration kind of what we're trying to figure out, right? We want to figure out what's going on as a function of time. So don't we want to know what's going to happen at some arbitrary time, sometime later? The way I'm framing it almost sounds like I kind of need to know in advance, how the configuration ends up, right? If it starts here and ends here, then I can employ this action integral. But actually, it's more general, and actually we can get away with solving these problems without having to know in advance what the final state is going to look like. Right? The logic here is that we're using the least action principle, right? That nature is optimizing the integral of the Lagrangian, in that nature is going to take the optimal path between two particular points, but we also have kept those 2 points to be completely arbitrary when we've been talking about them. We've not stated that it has to be up in the air and on the ground, but we're just saying that it goes from some point A to some point B. And by keeping it general, notice that Lagrange's equations pop out a very general differential equation that doesn't really at all take into account how the thing starts and ends up in configuration space. It is just a differential equation of how it will evolve through configuration space given a starting spot, and then either how it's going to end up, or you let that endpoint be arbitrary, right? What is the end state at some general time t later? So ultimately, the differential equations we get are going to be super general, that are not anchored in any way to a specific configuration, but they're general enough that we can then, for a given set of initial conditions, figure out what the configuration of the state is, or the system is, at some later point in time. All right, so that was just kind of an aside. That we keep talking about this configuration space stuff. But really, it's if we can write down the Lagrangian and employ Lagrangian's equation, or the Euler-Lagrange equation, that then allows us to get a differential equation that can then give us the true trajectory, for any arbitrary initial conditions or any arbitrary start and end point. And the idea, again, if you think of yeah, essentially, what we're trying to do is optimize the action integral of the Lagrangian. Which, again, the idea is that it's trying to, over time, right, cumulatively minimize or optimize, the liveliness of the system. So the idea of where nature is lazy comes from is that often, right, the integral of the Lagrangian, right, you're going to try to find what the minimum of that integral is. So overall, collectively, we are trying to find the path that ultimately minimizes the liveliness of the system, for example. But really, we should be saying that nature is doing some sort of optimization, because it's not always a true minimum. But I like the idea of thinking that nature is lazy. You'll sometimes see it written like that as, the principle of least action. Maybe another aside before I do one or two more examples. I could ask, can you derive the Lagrangian as being t minus u? Why I've kind of just stated that nature is optimizing an action integral of the Lagrangian, but I've never really stated why it should be t minus u. Why did nature decide that's what we optimize? Turns out you can actually derive that the classical Lagrangian for classical mechanics is just t minus u, but you need quantum mechanics in order to do it. So we can't really do it in this course. Let me point out kind of what's general and not general for classical mechanics. So in classical mechanics, all of classical mechanics can be derived on the assumption that nature is optimizing this particular Lagrangian, t minus u. Though I have stated that this idea actually is more applicable beyond just classical mechanics. In quantum mechanics, you can think of that the rules of quantum mechanics can be derived by an action principle, that there is some action integral of a Lagrangian that is being optimized. However, the Lagrangian there does not look like what we are writing down here. This t minus u really is the classical mechanics Lagrangian. The Lagrangian in other fields looks a little bit different. And in the limit of the classical regime, you can actually show that it becomes and breaks down to become something that is just t minus u, kinetic minus potential. But again, other branches of physics are still operating by doing an optimization of a Lagrangian. It just doesn't necessarily look like t minus u all the time. And if you're curious about the proof involves these things called Feynman path integrals, that were made popular by Richard Feynman. And the idea kind of what is going on deep down in the proof is that, in the realm of quantum mechanics, where you have a superposition of all these kind of different possible states, or in this context, you can think of, a superposition of all these various possible paths that an object can take to get from point A to point B, right? We've been kind of thinking classically and saying that nature picks one and that's what it does. And even that is not totally accurate, if we really want to jump into the realm of quantum mechanics. Because quantum mechanics says that in some ways the ball goes from point A to point B amongst all those possible paths. Right? It does take every single possible path of how you get from point A to point B. But it also can assign relative weights to all those possible paths, so that some of those paths are more probable than others. And what we then observe as humans observing the system is essentially the path that ends up being much, much more highly more probable than the rest of them. So in a sense, what we see is the most likely path, in a sense, in a quantum mechanical sense, of how an object goes from point A to point B. But quantum mechanics would say it's actually taking a superposition of all these possible paths as it goes from A to B. But that gets us a little too much into the weeds, so I will punt that for a graduate quantum mechanics course on the subject. But for us, we can think of the idea that nature is doing some sort of optimization, and it's optimizing this thing called the Lagrangian over time. So yes, you can derive, but need quantum mechanics and relativity and all that fun stuff. So let me do two other simple one-dimensional examples, and then the next couple of videos are then going to be focusing on kind of building up the complexity of the sorts of Lagrangian problems that we can do. So let me do a box on a spring. And everything's going to be horizontal. So I have a box that's attached to a spring, and I'm going to put my origin at the rest position of the spring. Meaning that when the box is located at the origin, the force from the spring vanishes. But again, now we're getting completely away from forces. I don't really, am ever using forces at all. The dimensionality of this problem is 1. So my general coordinate that I might use in this case is going to be, say, x, right? The location from the origin to the location of the box. If I specify that, that specifies everything about the system. What about the vertical direction? Isn't there a constraint? Yes, that's what keeps the dimensionality 1. But notice with the Lagrangian formulation, I don't even need to take that into account. Like, I don't have to talk about things like normal forces or anything like that. We'll get to that as how you can actually try to introduce that stuff back in. But generally, any sorts of geometric constraints can just be folded into the equations you solve to write your Lagrangian in terms of the minimum number of variables you need. So in this case, the kinetic energy is going to be 1/2 mx dot squared. Potential energy is going to be 1/2 kx squared. Because again, I'm putting the origin where the force vanishes. And remember, that's, before we wrote 1/2 k x minus x naught all squared. But I'm putting the origin essentially where x naught is. So then the Lagrangian looks like it's 1/2 mx dot squared minus 1/2 k x squared is my Lagrangian for this particular system. And again, I have that the partial with respect to now x is my variable, is then going to be equal to the time derivative of the Lagrangian with partial with respect to x dot. So then, partial with respect to x looks like it's then going to be negative kx. Kind of looks like a force. We'll come back to that. And the partial with respect to x dot looks like it's going to be mx dot. And then when I take the time derivative, that then just becomes mx double dot. And once again, lo and behold, what does Lagrange's equation imply? That negative kx, which is that, is then equal to mx double dot, which is the right-hand side of Lagrange's equation. Or that x double dot plus k over m times x equals 0, which is exactly what we had written down before for simple harmonic motion, that this box undergoes simple harmonic motion, and for a given set of initial conditions, you can write down exactly what that path looks like. Again, pretty cool that this is all kind of just popping out naturally under the idea of nature doing an optimization. We've never had to once define a force. As long as we can write down kinetic energy and potential energies, we're off and running. You might say, well, to define kinetic energy and potential energy, we define those by integrals of forces over distances and stuff like that. True. But really, right, that's just saying something about the specific formulas we've written down for kinetic energy and potential energy, right? We could have started very generically with potentials and kinetic energies and arrived at some very similar conclusions if we wanted to start with Lagrange compared to start with forces at the beginning of the semester, say. Let me do one more. That brings in this idea of generalized coordinates. And I will state without proof that you can apply the Euler-Lagrange equation for any general coordinate. It does not have to be a Cartesian direction, for example. And I will omit the proof, but I think your textbook goes through the proof. Right, given some general q, right, so this is your coordinate, your generic coordinate, you can write, say, the Lagrangian t minus u as some function of q, q dot, and t. And then you can apply the Euler-Lagrange equation and then solve the partial of L with respect to Q equals the time derivative of the Lagrangian with respect to Q dot. And that still, when solved, will give you how the configuration changes when it's written in terms of coordinate Q, which again does not necessarily have to be a Cartesian coordinate. Let me do that example, and then we can call it for this video. So let me do the simple pendulum. So we have the simple pendulum that swings, and there's some angle theta here. And I'm going to put my origin at the top of the pendulum. The dimensionality of this problem is still 1. While it can move in x and y, right, there is some x and y coordinate that define the position of this bob. But because of the constraint of the fact that x and L or x and y are located at positions defined by capital L, I can write this in terms of a single coordinate. I could write this in terms of just x, or I could write this in terms of just y. Or I could maybe write this entire thing in terms of theta. Maybe I'll use that. So I'm going to use Q as my theta coordinate instead. So then the goal is I have to write the Lagrangian in terms of theta, its derivative, and maybe t by itself, if t appears by itself. So the first thing I would do is, can I write the Cartesian coordinates in terms of my particular variable? Because let me just write in Lagrangian first. Lagrangian t minus u. I know that's going to be 1/2 mv squared minus, right, mgy, for the potential energy. But then v in this case, I know is going to have both x and y. So this is going to be x dot squared plus y dot squared minus mgy. Right, because that's going to have the scalar velocity, right, is just square root of the sum of the squares of the x velocity plus the y velocity squared plus the z velocity squared, etc. So it's written, depends on x and y and its derivatives. But I can rewrite everything in terms of q. So for example, if I look at the above example for the pendulum, x in this case looks like it's just L times sine of theta, because x is just this distance here. So it's one side of this triangle. Then y in this case, and I have to be careful about my origin. My origin is up top, so it looks like y in this case is negative L cosine of theta. Because if the origin is here, then y is this value here, which is currently negative relative to the origin. All right. Since x dot and y dot are involved, I'm going to have to evaluate x dot, which looks like it's going to be L cosine of theta times theta dot, again by the chain rule. I'm taking a time derivative, not a theta derivative. And then y dot looks like it's going to be L sine of theta, theta dot. All right. X dot squared looks like it's then going to be L squared cosine squared theta, theta dot squared. Similarly for y dot squared. And then notice when you add them together, you end up getting cosine squared plus sine squared, which is 1. So then it looks like x dot squared plus y dot squared is going to be L squared theta dot squared. And if you're thinking that's kind of what I anticipated from polar coordinates, because it's restricted to always be a distance L away from the origin, exactly, right? We could have also started in polar coordinates and wrote down the velocity that way, right? Then the velocity would have been r dot squared plus r plus theta dot all squared. But since r is not changing, right, it would have just became what I wrote down. So now it looks like the Lagrangian is what? It looks like it's 1/2 m L squared theta dot squared minus, well, I guess now minus plus mg, but then y is negative L cosine theta. So that's why it becomes a plus for the Lagrangian, because there's two minuses there. Now I've written the entire Lagrangian in terms of my one coordinate theta. The Euler-Lagrange equation says that the partial with respect to theta better equal the time derivative of the partial with respect to theta dot. So then, partial with respect to theta, that looks like negative mgl sine theta. No theta dot, because again, this is a derivative with respect to theta, not time. Then with respect to theta dot, looks like I have the 1/2 m L squared, goes along for the ride, and then a 2 drops down, and this becomes 2 times theta dot. So then the 2's cancel, this looks like it's m L squared theta dot. The time derivative of this, m L squared theta dot, m and L is a constant, so this looks like it's m L squared theta double dot. And the Euler-Lagrange equation says m L squared theta double dot equals negative mgl sine of theta. See, m's cancel. One of the l's cancels. I can bring everything to the other side, divide by L, and notice I again get g over L sine of theta equals 0, which, lo and behold, was exactly the same thing we got when we did a whole messy Newton's second law torque analysis, or when we did Newton's second law in polar coordinates, and we had tensions we had to worry about, and what sign is torque again, and all this just pops out so naturally when we throw it through the machinery of the Euler-Lagrange equation. Really just remarkable. And so moving forward, what we're going to do is, how can we do this for configurations that are not just single dimensions, that might have multiple coordinates in it? How do we solve the Euler-Lagrange equations for those? And maybe if we have time, we can start thinking about, what if I wanted to learn something about the constraints that are in these sorts of problems? Like, notice here, there's absolutely no way I can say anything about the tension that's in the rod. You might say, well, that's something that Newton's laws allowed us to do, but I can't do it with Euler-Lagrange, so maybe there are advantages to one over the other. There are ways that you can reintroduce these geometric constraints and learn something about what's going on with them. And we also need to think about whether or not there is actually an equivalence between what I'm doing here with Euler-Lagrange and Newton's laws of motion. Or maybe it's just I'm just getting lucky and they just happen to give me the same answer. No, actually, it turns out you can prove that they are equivalent formulations. All right, very good.